Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you, Jean-Han. Is this on? It's always a pleasure to be back at Microsoft. I want to talk about the Erdos-Renyi evolution. This was developed in 1960, but it just continues to fascinate and evolve in a certain way, and I have a somewhat different perspective on it than usual, and I think it's good to have several different views of the giant component. So let me begin with some background. So Erdos and Renyi in 1960 looked at the random graph GNP. That is, you have n vertices, and between each pair of vertices you put in an edge with probability p. And well, they looked at many different aspects, but in particular they looked at the parameterization p equals c over n, which you may think of when p equals c over n, that a vertex, you think of c as a constant, like 5, that a vertex on the average has 5 neighbors. Not exactly 5 neighbors, but on the average it has 5 neighbors. And Erdos and Renyi, in their original paper, noted that the nature of the random graph is very different depending on whether c is less than 1, or c is greater than 1, or c equals 1. And from the perspective of mathematical physics, we can think of this as a percolation that takes place at the critical point c equals 1. Once again, it's helpful to think of c as the average degree of a vertex. What happens is, in the subcritical phase, that is, if c is less than 1, now by less than 1, I mean c is a constant less than 1, 0.99, but then you're looking in the limit as n goes to infinity. If c is less than 1, then all of the components are very small. The largest one is logarithmic size. But basically, they're all really small. And in fact, they all have simple nature. They're all trees or unicyclic. Like most of them are trees. But if c is greater than 1, say c equals 2 or 1.03, then there is a giant component. And this giant component has a positive proportion of the vertices. So if you think, as Erdos and Renyi did in the very title of their talk, of the evolution of the random graph, you think of c increasing and you're getting more and more edges, then at c equals 1 you get this very sudden change, where for c less than 1 you have all these small components, and then very quickly they all merge together, or many of them merge together, to form this giant component. The giant component has a constant proportion of the vertices. That constant's given by y, where y is that number less than 1 that satisfies 1 minus y equals e to the minus cy. That's given by this implicit formula. So y is a function of c. If c is less than 1, y is 0. There is no giant component. And then y is a continuous function of c. It approaches a limit of 1, that is proportion 1 of the vertices as c goes to infinity. At c equals 1, the slope from the right, not quite the derivative because the function is non-differentiable at the critical point, but the slope from the right is 2 in the language of mathematical physics. This is not a first-order phase transition because the function y is continuous as a function of c, but it is second-order phase transition. We further know that the average degree of the vertices in the giant component is c plus d. So now c is greater than 1 for the rest of the talk. Is c plus d, where d is what's called the conjugate of c. D is that unique number from 0 to 1 that satisfies d e to the minus d equals c e to the minus c. If you look at the function, let's see if I can draw it. If you look at the function x e to the minus x, it hits a maximum at 1. And so for any c greater than 1, there'll be a d less than 1, a unique d less than 1, such that c e to the minus c is d e to the minus d. And this conjugate comes in a variety of places. We further know that there is a critical window, and much of the more advanced work of the last 20 years is dealing with this, that is at c equals 1, the correct parameterization is to write c equals 1 plus lambda n to the minus 1/3, and then as lambda goes from minus infinity to plus infinity, well, that would be another talk. Fascinating topic, but I will not be talking about the critical window today. So I will be looking at a fixed c that is greater than 1. So think of c equals 5. So we have the p equals 5 over n, and we want to look at the giant component. And in particular, what I will show is, let's look at the giant component, or sorry, actually here, let C of v be the component containing the vertex v. Fix some vertex v and look at its component. But while that component could have just 4 vertices, or v could be isolated, the case of interest will be when v is in the giant component. That's what I'll be talking about. So let C of v have x vertices and x minus 1 plus w edges. Why do we write it this way? Well, if it was a tree, it would have x minus 1 edges. So w is the number of edges beyond being a tree. C of v is connected, so it has to have x minus 1 edges. So let's just define those random variables x and w. Then what's known is the giant component has asymptotically yn vertices, and the number of edges it has is asymptotic to c plus d over 2 times yn. And what I will get is some local statistics on the number of vertices and the number of edges, that the probability that x equals k and w equals l is going to be some explicit constant c star and inverse, where k and l are the usual values for the number of vertices and edges of the giant component. Sorry, L is not quite the number of edges. It's edges minus vertices. There's always that x minus 1. Y is the number given earlier. Yeah, thank you. Y is the size of the giant component. So we're fixing C. C is 2. Y is this number. So that will be the proportion of the points in the giant component. So it's given by that. It's well defined. It's well defined.
This holds asymptotically whenever k is asymptotic to yn.
No, that's a good question. I'll have to be a little bit tighter than that. K will have to be very, very close to yn. Yeah, but that's a good question. Well, it's not a really good question because I don't know the answer to it, but it's certainly worth asking. It's a very good question to ask. Yeah, I mean, I'd like to know throughout the range of K and L, but I'm only going to take K that's really right on the button for it. Now, the heart of this is a new way of looking at the giant component. So this is the most important slide in the talk. I want to generate the component containing the vertex V in the random graph. And I'm going to generate it in an unusual way. So this is really the heart of it. Here I've given an illustration with 7 vertices. V is just specified. Yeah. No, okay. And then the other vertices, A, B, C, D, E, and F. I define the following random procedure. Let's call V the root. All of the non-roots, A, B, C, D, E, and F, flip a coin n minus 1 times. N is just the number of vertices in the graph. Flip a coin n minus 1 times, and these coins come up heads with probability P. So that's going to be my underlying probability space. This I'll call the flip matrix. Okay, so here we have these coin flips. Now I'm going to generate the component containing the vertex V. And I'm going to put on my computer science hat, and I'm going to do it by breadth first search. So I take the vertex V, and V looks for neighbors. But we're going to look at it in a little bit of a different way. Instead of V probing for its neighbors, imagine that all of the other vertices are trying to get into the component. Rather than trying to spread the component out, we have the other vertices are all trying to get in. So first, we do the breadth first search. V looks for neighbors. The other points, A, B, C, D, E, and F, they look at their first coin flip. If their first coin flip was a head, they're adjacent to V. So each one is a head with probability P, so all of those edges are there with the probability P that you want. So in this case, we look at the first coin flips for each vertex. B and D came up heads, so B and D are adjacent to V. Now, again, in the language in the computer science language, we started with a stack consisting of V, and B and D are adjacent to V, so if we pop the stack, V disappears from the stack, and now the stack consists of B and D. So now Y will represent the total stack size. The total stack size is now 2, because we've popped off V and we've added 2 new vertices. Z will represent the number of new vertices that were brought into the stack when we did this. Okay, so V is adjacent to B and D. Now we continue our breadth first search. Now B looks for neighbors. We pop the stack. B's at the top of the stack. B looks for neighbors. How does it look for neighbors? It doesn't look out for neighbors. The other points are trying to get in. So what do? We look at the second coin flip. It's an independent coin flip. We look at the second coin flip. We see if it's a head. And when it's a head, that means that that vertex is adjacent to B. So here, in the second coin flip, A came up heads, so A is adjacent to B. We've popped the stack. B's disappeared from the stack, looking at the second row. The stack now consists of D and A. Right. Then we go down to the third row. So we pop the stack. D looks for neighbors. We look at the third row. We look for heads. Well, there is a head there, but it doesn't count. The only heads that ever count are the ones that are the first head in a column. Was once you've had a head, you're already in the stack. The later heads don't count. They don't count. Still, it's very useful to have an underlying probability space where you have this independence. So in the third row, no new vertices enter the stack. So D has no neighbors in this breadth first search tree. And, okay, so now the stack consists of A. Now A looks for neighbors. In the fourth row, F comes up with a head, so F is adjacent to A. All right, now the stack consists of F. In the fifth row, we have all tails. So F finds nobody, and so that ends the component. F, the breadth first search is over. The stack is empty. The breadth first tree is the green tree over there. There's an interesting point here. If you look at the sixth row, C and E say, wait a minute, we want to join. Sorry, too late. Too late. We've already closed up shop. The component is over. This is what is often called fictitious continuation. And it's a very powerful idea because, as you'll see, it allows us to compute things. So the probability space, each vertex makes the n-1 coin flips, even though later on we may not make use of them. We may not make use of them. Yeah?
So your stack is a queue, not a stack.
Sorry?
The first one that goes in is the first one that goes out.
Oh, maybe it's not a stack. It's a queue.
It's a queue.
I always confuse those two. All right. It's a...
The graph is not always true, yeah?
Sorry?
The graph is not always true.
No, there are other edges in the graph.
No, this component is not necessarily a tree. It can be any shape.
That's right. What we are finding is the breadth first tree. There, and we will talk about the possibility of other edges. Exactly. So we have not found all the edges, but what we have found is the breadth first tree. And indeed, when you do breadth first search, you don't find all the edges. You just find the breadth first tree. But later we'll go back and look at it and search for other edges. So let me take this. So I should mention that this thing, my apologies for confusing stack and queue, but it turns out we could have done this as a stack and it would have had the same probabilities. It really doesn't matter which point we pop out of the list. We still get the same dynamics. So we could do depth first search or breadth first search or alphabet and any kind of search, and we'd still get the same thing. So all right, here it is. So this is what I said before, only I'll give it some words. Let's call this the flip matrix. There's just for coin flips. I haven't come up with anything more clever yet. So for each non-root W, it flips a coin n-1 times, and I said it equal to 1 if it comes up heads, and they come up heads with probability P. Now, so that's our underlying probability space. For a vertex W, let T sub W be the first J for which the coin flip came up heads, but that might be undefined. That's fine. There might well be all tails. No problem there. Because what we're really interested in, let Z sub J, for J equals 1, 2, 3, ... be the number of W for which their first head was on the jth flip. Their first head. Remember, the later heads don't count. So we look, Z sub J is the number of vertices whose first head is on the jth flip. So this is the number of vertices that enter the queue on the jth attempt. So if we look at the stack size, the queue size, I'm going to say stack, even though it should be Q. If we look at the stack size, it starts out as 1, and then we have this natural recursion. The stack size, at each time, we pop the stack, so it goes down by 1, and then how many more vertices do we add to it? Well, that's what we call Z sub j, Z sub j. And what is the size of the component? It's the first capital T when the stack size becomes 0. And so this is all tautological. There's no probability here. You will do the breadth first search. The component size will be the minimal T for which the stack size is 0. But we have this fictitious continuation so that what happens is YT, the YTs are formally defined, so maybe they go 0 and then they go a little bit negative and then they're 0 later and then they're positive. All sorts of things might happen. But the actual size of the component is the smallest T for which Y sub T equals 0. Just to give a simple example, suppose the first row is all tails. All right. Well, then Z sub 1 is 0, and the process ends. We had an isolated vertex. So Z sub 1 is 0, so Y sub 1 is 0, so the component size is 1. Even though later on, Y sub 5 may be 37. But sorry, too late, guys. You can't get into the party. We already closed down right at the start. Now with this, let's look at the size of the component that we get, which we call capital X. Now, there are two. Let's look at the probability that the component has size k. Now, there are two conditions on the component having size k. Y sub k has to be 0, and no previous Y sub k can be 0. Y sub k can only go down by 1, so if it ever goes negative, it has to be 0 before it goes negative. So we don't have to worry about it jumping over 0. All right, let's look at the statement exact, which is that Y sub k equals 0. This we can do precisely. This is binomial. Let's look at the first k rows and look at how many columns have a head in the first k rows. Well, each W, the chance that it's not all tails for the first k rows is 1 minus p to the k. So the chance that it has at least one head, it might have 5 heads, the chance that it has at least one head is 1 minus p to the k. But we have total independence of all these coin flips, so the number of columns, so the number z1 plus dot 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 plus zk, each W has a head in the first k rows with probability 1 minus p to the k. So the total number of W's that we're counting here is simply binomial. These are independent over the different W's. Binomial distribution n minus 1, comma, 1 minus p to the k. And that's the exact distribution for z1 plus dot 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 plus zk. But notice we had this fictional continuation comes in here. We're not stipulating the z1 plus dot 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 plus zk. The things might have stopped well before, but we're still defining it anyway. All right, now, up to now, this is true for any n and p and k. But now I'm going to specify that, and this, I think, answers some of the question about how close to the critical value we're going to look at. I'm going to specify that n, p, and k have the property that the expected value of the binomial distribution is k minus 1. And if it's very, very close, it would be okay as well. All right. So let me specify that n minus 1 times 1 minus p to the k equals k minus 1. And let me set y equal k minus 1 over n minus 1, which is 1 minus p to the k. If p is c over n, then, and if we estimate 1 minus p by e to the minus p, then basically we get the equation y is very, very close to 1 minus e to the minus cy. So this is the y that is the y that's known from giant components. So we're going to be looking at that specific value of k, at the probability of the giant component having exactly that size. Okay. Well, the first condition is the condition exact. What is the probability that the binomial distribution, which has expectation k minus 1, hits k minus 1 right on the nose? That we can solve. We've got Stirling's formula. We go through, we get the solution, and the solution is constant times n to the minus 1/2, where the constant is over here. Okay. This is like the standard problem. If you flip a million fair coins, what's the probability that you get exactly 500,000 heads? And the asymptotics are constant times n to the minus 1/2. But this comes out very nicely using Stirling's formula. Okay. So the probability of being exact, that we've got, that we know. But that's not the whole picture. All right. Now, let me look at the expected stack size at time as a function of j as simply this function. I'll just replace the k by a general j. So this is the expected number of points in the stack at time j, because it's there are n minus 1 possible points. Again, this is always with fictitious continuation. The probability that w has entered that w has had a head is 1 minus p to the j. We've popped j points off the stack, and we started with 1. So this is the exact formula for the expectation. If we look at this function, well, it's 1 at 0. I mean, we start out with a stack at size 1. We've cooked the books so that at k it's 0. That's how we defined k and p and n. And if we look at this, it goes up and it goes down. Okay, I mean, we do a little bit of analysis. And one of the things is that when j is near 0, the derivative, or if you like, ESS of j plus 1 minus ESS of j, discrete derivative, is around c minus 1, which I think of as positive drift, because this is expectation. So what's saying is that the expectation is moving up. But of course, there's fluctuation. It's a random process. And when j is around k, it comes out to be d minus 1, which is negative. Well, it goes up and it goes down. And when you work it out, this corresponds to what people in random graphs call the duality principle. This is a wonderful property. So I'll just state it if you haven't heard it before. It's just a wonderful thing. If you take the random graph with probability c over n, and if you throw away the giant component, it looks like a random graph on some n prime vertices with probability d over n prime, where d is the conjugate of c. Very, very nice kind of thing. And that connects to this in some ways. So, but anyway, you can make the calculations, and you see that the derivative around k is d minus 1. It's going down. So that's the expectation. Now, what we're worried about, we're going to condition, if we have the property exact, that you get exactly that z1 plus dot dot plus zk is k minus 1, but we're worried that we might have stopped earlier. And we break this into 4 parts. Either we stopped very early, which we call left, that is that I think I got the inequality reversed. These are the, because I want left to be the bad event. Yeah, I think this should be less than. I think I got the inequality. I got the equality reversed. The bad event is that in the first t times we only got t minus 1 or fewer points, because then we would have stopped earlier. So, and then left middle is the, and I take it up to log squared n, which there's a lot of room for that, but some kind of, because I'm going to have 2 different arguments, depending on things dying out right near the start or sort of in the middle. Now, if we go to the right, we could say z1 plus dot 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 plus z sub k minus s, but since we're going to be conditioning on exact, see, if we know that z1 plus dot 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 plus zk is k minus 1, then the condition at k minus s, instead of looking at the first k minus s terms, just look at the terms from k minus s plus 1 to k. And then the condition turns out to be that those numbers are, I think I reversed that one too. I think this That's so. All right. Okay. Yeah. Yes. Yeah. I wanted to express that it stops before s. So, for example, if z sub k were 0, it would have. Yeah. Take s equals 1. If suppose z sub k were 0, then it actually wouldn't have stopped at k. It would have already stopped at k minus 1, because on that last turn we picked up 0 points, so we would have stopped before. Okay, I hope I have this right without. It might be off by some plus 1s, but I think this is right. Yeah. K is the total size, so I'm assuming. Yeah, you have the z1 plus zk. K is the total size. And what we're worried about is that z1 plus dot dot plus zt is less than or equal to t minus 1. But instead of writing z1 plus dot 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 plus zk minus s is less than or equal to. Oh, yeah, you're right. Sorry, yeah. Thank you. Yeah. Yeah. Okay. All right. So these are the problems. Now, if you're in the middle, whether it's left middle or right middle, we can use some large deviation bounds and say that the probability of failure is extremely small. Because basically what we have is a binomial distribution, and we know that a binomial distribution minus a constant. And we know that the expected value of the binomial distribution minus the constant is fairly large, because we have this function ESS of t, and it's fairly large. And what we're asking for, the disaster, is if it's less than or equal to 0. So that's a large deviation result. And one can use basic large deviation results, for example, the Chernoff inequalities. Now, they don't work if you're very, very close to one of the edges. But this log squared n turns out to give us lots of room. And so I haven't done it here, But one can show that the probability of failure of left middle or right middle for any particular t or s is lower than polynomially small. In fact, it's like n to the minus log n. It's something like that. But let's just say it's n to the minus 50. Well, that's plenty small for us. Now here's an interesting thing. We have to multiply this by, let's say, n, because they're at most n values for t and s. But furthermore, we want the probability of failure conditional on things being exact. But we're conditioning on a probability that's n to the minus 1/2. So that can't increase the probability of failure by more than a factor of n to the 1/2. So if the probability with no conditioning was n to the minus 50, it's still really small. So what happens is, and I'm saying this a little roughly, but basically we have the expected stack size, and once it starts going, it's not going to go down to 0. It's not going to go down to 0 in the middle, except right near the end, when it does hit 0, it might hit 0 before. Now, suppose we condition on the statement exact. What is that conditioning? It says that we have k minus 1 vertices, w1 through wk minus 1, precisely k minus 1 vertices. Each one of them is not all tails in the first k rows. But other than that, it's the probability it was. So the probability that the first head is on the jth time is p times 1 minus p to the j minus 1, which is what it was before, divided by y, because we're conditioning on this event that happens with probability y. So that ups it by y inverse. So we actually know exactly the distribution, this conditional distribution, on all of the TWs. And the columns are independent. So we've lost the independence of the coin flips, because in a given column we have to have at least one head. But we still have the independence between the different columns. The different W's are working completely independently. Now we define Z1 through Zj as before. They're the number of columns in which there's a head in which the first head appears at the jth time. Now the calculations we had before about positive and negative drift come into play. When we do the calculations, when j is small, like 1, the expectation of Z sub j is C. That makes sense because you look at the first point, it's going to expect C neighbors. And when j is near the end, near k, the expectation is this conjugate D. And so we're going to have this number D. Now, the ZJs are not quite independent because we know that Z1 plus ... plus ZK is exactly k minus 1. But they're pretty much independent. Well, that's the part I tell you the truth. I haven't worked out the details. I'm sure it's okay. So how can things go wrong? Things can go wrong near the start and near the end. What's happening near the start? The stack size starts at 1. Each step, what happens to the stack size? It goes down by 1 because we popped the stack, and it goes up by Poisson C. Now, eventually that Poisson C is no longer accurate, but that's why I took care of the middle separately. So I'm only looking near the start. So what we have is basically a walk where at each step we go up by Poisson C and we go down by 1. And what we want to do is escape. We don't want to hit 0. Because if we hit 0, that means that we've aborted early, that we actually have a very small component. So, for example, the prime example of that is if the initial vertex is isolated, Z1 is 0, which happens with probability e to the minus c, we just go right down to 0. All right, well, this is a nice probability question. Let the walk be infinite. Here's a nice probability question. Take an infinite walk, start at 1. At each step, go up Poisson c and go down 1. What is the probability that you ever hit 0? Turns out the answer is y. This number y that we've been talking about. So let's just allow that. So the probability of escape, that is that you never hit 0, is y. Now what about on the other side? Well, on the other side, we hit 0 at k. We're worried about hitting 0 a little bit before k, like maybe at k minus 3. Well, here it helps to reverse time and think of starting at k and just flip the axis a little bit. And when we do that, we have the following walk, because we've reversed things. We start at 0, and at each step, instead of subtracting 1, we're adding 1, because we've flipped our perspective. We're adding 1, and we're subtracting Poisson d. So what had been negative drift, it's easy to turn negative drift into positive drift. You just switch your time axis, and so that's what we've done. So okay, so now we have another interesting probability question. Start at 0, each step add 1 and subtract Poisson d. What is the probability that you never get back to 0? Because if you do get that, so this does have positive drift because d is less than 1. If you ever do get back to 0, say in time 5, that corresponds to the actual component size not being k, but rather being k minus 5. All right. And that turns out to be 1 minus d. And so, and then one needs some stuff about them being independent. And so it winds up, you get the local statistics on the size of the giant component. It's this constant times n to the minus 1/2. Now, as was pointed out, we don't have all the edges of the giant component. All we've done so far is we've calculated the breadth first search tree. Now, when you calculate the breadth first search tree, you have explored some pairs in this component, but you haven't explored all of them. Which pairs have you not explored? Let m be the number of pairs in the component that you haven't explored. Well, you haven't explored whether B is adjacent to D, because first V found B and D, then B looks for its neighbors, but it doesn't look for D, because D is already in the stack. Then the stack consists of D and A. D looks for neighbors, but it doesn't look for A because A is already in the stack. So when you do the breadth first search, what are the pairs that you haven't looked at? It turns out when you do breadth first search on this random graph, the pairs that you haven't looked at are exactly the pairs W, W prime, where when you pop the stack with W, W prime is in the stack at that time. But one of them has to be popped first. All the vertices get popped. Let W be the first one to be popped. So W's popped. If W prime is not yet in the stack, then it's examined. W's looking for neighbors. The only vertices that W doesn't look for are the points that are already in the stack. And we've ordered this so that W is the one popped first. So the things unexplored are the pairs W, W prime, where when you pop the stack with W, W prime is in the stack at that time. How many points are there? Claim is it's given by this formula. Well, when you pop the stack, with W, you count really the size of the stack minus 1. You don't count W itself. But we're summing that over all W. So what we're doing is we're summing the stack size minus 1 from I equals 1 to k minus 1. And it's interesting, M is like an integral. We have the stack size as a function of time, and we're basically taking well, it's a discrete thing. We're basically taking the integral of the stack size as a function of time. But how can we sum the stack size as a function of time? Well, what we can do is for each W, add how much time it spends in the stack. How much time does W spend in the stack? It comes into the stack at time t sub W. It leaves the stack at some time t sub W plus. So its total time in the stack is t sub W plus minus t sub W, maybe with a minus 1 there, and we have to add that over all W's. But the thing that saves the day is that popping the stack, exactly one vertex is popped at each time. So the sum of the t sub W pluses, the times when points leave the stack, is just 1 plus 2 plus 3 plus 4 up to k. The only thing that we're unsure of is when points enter the stack. And when we do this, we get this nice formula that the number of unexplored vertices is k times k minus 1 over 2 minus the times when the points enter the stack. Just to give you another example of this, when imagine that the breadth first search was a path, the breadth first search tree was a path. All right, then there would have been no unexplored vertices, and what would have happened is that the ith vertex would have entered the stack at time I. The sum of the t sub w's would have been k times k minus 1 over 2 would get 0. So once again, if the breadth first search tree is a path, then M is 0. So we get this nice formula that M just depends on the t sub w's. And now we can get a nice distribution for M. We can use the central limit theorem to get the distribution for M, the number of unexplored edges. Well, remember I said it was the summation of t sub w minus this constant. Well, the t sub w's are really this truncated exponential because we're assuming that t sub w has a value between 1 and k. So it's a truncated exponential distribution. So each t sub w we could calculate. It has some expectation, some constant n. It has a variance on the order of n squared. But the if we condition only on exact, now the t sub w's are totally independent. So we have the central limit theorem. And M, the number of unexplored edges, is a normal distribution with a certain mean on the order of n squared and a certain variance on the order of n cubed. It's conditioning only on exact. Yep. Because we're only conditioning on exact. We're not conditioning on, this is, you've hit the subtle point, well, maybe the cheating point, if you like. If we condition only on exact, then each column, what we're saying is that there are k minus 1 columns, and each column is not all tails. But other than that, but the separate columns are independent. And that's why. That's why. And at the end, I'll make some comments about why that doesn't hurt you too much. So now I want to specify the number of edges to be, all right, now, that's the number of unexplored edges. The actual number of edges beyond the breadth first search tree itself, each one of those unexplored ones is then, now we explore them, they're in with probability C over n. So the distribution for W, the number of edges beyond the breadth first search tree, is binomial m comma C over n, where m itself has this distribution. So it's a double distribution here. But m is given by the central limit theorem. We specify L to be right where it should be, where we expect the number of edges to be. And now we look at this. M is normal. And there are actually two things contributing to the probability that W equals L, because we have this binomial m comma C over n. Now, if m were precisely alpha n squared, we'd get a normal distribution. But furthermore, m itself has a normal distribution, which we're then multiplying by C over n. It turns out the two things scale to the same result, and they both come in to the normal distribution. So it turns out that W has a normal distribution whose variance is n times a constant, and one gets a local limit theorem. Let me just state kind of an interesting general point here. Here's sort of the scaling. I hadn't seen something like this before. We have an m with a central limit theorem, and m is on the order of n cubed, and it has a variance on the order of n cubed. And let me recall that W is binomial m comma C over n. Okay. And there's an interesting general result here. Given the central limit theorem for n, we actually get the local distribution for W. I mean, if we knew that m was exactly some value, we'd have Stirling to get it. But actually, as long as we know that m has the central limit theorem, we can get the local distribution for W. But we have to be a little bit careful with the scaling, because two separate things come into the variance that both scale the same way. M can be off by n to the 3/2, which would knock W by n to the 1/2. Or when we take the binomial distribution, we've got, sorry, this is n squared, not n. Also, when we take the binomial distribution, n squared comma C over n, just looking at the scaling, we can be off also by root n there too. So we have two things that are both affecting the distribution. And we get this. And then I've got some further arguments, which I think I'll skip at this point, about arguments for why the further conditioning of the fact that near the start and near the end things were good does not asymptotically affect things. But let me quickly move on. So if we put all of this together, what we get is the local statistics for the probability that the component of V has exactly k vertices and L edges. And it's this some constant which we've computed times 1 over n. But again, I emphasize this analysis is only valid when k and L are really right on the button, or pretty close to the values that you should have for the giant component. If you want to know what's the probability that the giant component where you think it has n over 10, probability that it has 2n over 10 vertices, this won't do it. This won't do it. Yes. Now, what happens is, in fact, there has been work on this. The fluctuation is that it is a normal distribution. Let me not talk about large deviations, but basically it's a normal distribution The scaling is by square root of n.
So are you allowed to take such?
You are. I haven't examined it fully, but I believe that if you adjust k and l by the order of root n, you should be able to get something. But of course, the constant will change because this I definitely want to explore. Yeah, I definitely want to explore. Yeah. Let me close though by the original impetus to this, which was a marvelous result due to Bender, Canfield, and McKay. And this argument gives an alternate proof to their result, at least in certain regimes. I'm not sure how widely it can be done. Here was the problem they examined some 13, 14 years ago. Very basic enumeration problem. Let C of KL be the number of connected components, labeled connected components, with k vertices, k minus L plus 1 edges. Just enumeration, no probability here. Well, when L equals 0, k to the k minus 2. It's Cayley's formula. What Bender, Canfield, and McKay did was they found the asymptotics for C of KL for the entire range of k and L. As long as k goes to infinity, L can be anywhere, and they have the asymptotics. And it was really a brilliant piece of work that involved looking at a recursion and a very detailed analysis of the recursion. Let me restrict myself to the case where L is on the order of k. So for example, how many connected components are there with k vertices and 2k edges? Well, here's a way to do it, and you don't have to be as good as Bender, Canfield, and McKay. In particular, there's no recursion. It's really a direct argument. Anyway, I like the argument, so this is what got me started. We reverse engineer. We pick n and p so that when you look at the random graph GNP and you look at its giant component, it's likely to have k vertices and k minus 1 plus L edges. Now, can you do that reverse engineering? Yes, you can. Yes, you can. Proof by intimidation. Yes, you can. At least in this range, you can. All right.
So,
Yeah. Yeah.
When you're saying counting connected components,
Yeah.
you're saying just connected graphs.
Oh, yeah. Yeah, you're absolutely right. This is what happens with the first time one gives a talk. You're right. Yeah, the problem is counting connected graphs. Yeah, there's nothing about components in the original problem. Right. So here's how we attack it. We reverse engineer and find n and p such that k and L are these likely values for the number of vertices and k minus 1 plus L for the number of edges of the giant component. Now we know that the probability that the component of V, some fixed root, has exactly k vertices and k minus 1 plus L edges is this constant C star times n to the minus 1. But on the other hand, what is the probability that the component of V has precisely k vertices and k minus 1 plus L edges? Well, this formula is the exact formula, because for its component to be that, we pick the other k minus 1 vertices, n minus 1 choose k minus 1 ways. Then we pick the connected component on those k vertices. That's in C of KL ways, because that's the definition of C of KL. Now, having picked those, all of those have to be edges, so that's p to the power k plus L minus 1. And then further, we have a whole bunch of things that have to be non-edges, So that's 1 minus p to a certain power. And what is that power? Well, these k vertices and the remaining n minus k cannot have any edges between them. Otherwise, it wouldn't be the whole component. So it's k times n minus k. And furthermore, there are no more internal edges. So we have to add another k choose 2 minus k plus 1, k minus 1 plus L. Well, okay. Looks a little messy, but if we look at this, this equals this. C star n to the minus 1, we know this. This is analytic. This is analytic. This is analytic. All we have to do is, the only thing that's left open is C of KL. And so we solve for C of KL. So let me end with an aesthetic comment here, a comment on aesthetics. You'll decide whether it's an aesthetic comment. When I think of probabilistic methods using random graphs, to me, the most pleasing cases are where you use random structures, but you end up with a solution to a problem where the statement of the problem does not involve probability in the statement. And to me, this fits the criteria, because C of KL is a well-defined function. It's an enumeration problem. There's no probability in C of KL. But with this approach, in order to get the analysis of C of KL, we create this probability space. We reverse engineer it so it just fits just right. And then we go through all this hocus pocus, and what we wind up with is an alternate proof of this wonderful theorem of Bender, Canfield, and McKay. So I think I'll stop at that point. Thank you. Yeah.
Yeah, so you're assuming the graph is symmetric or undirected edges?
Yes, yeah, I should have said that at the beginning. This entire analysis is for undirected graphs, and the symmetric, I guess, would be, I just call them graphs, but they're undirected, there are no loops, and there are no multiple edges. And one can naturally ask similar questions for other classes. Yeah.
You also intend to assume that any finite component with K and L come up uniformly in your construction.
Sorry, say.
Your construction will give calculate the probabilities and then
Yeah.
count the KL. You're assuming that any graph that has this property will come uniformly in your construction. So otherwise, I might not be counting.
I don't think so. Any. Well, anyway, I think it's true. It is true. Yeah. Well, these are labeled. These are labeled.
They're sort of labeled, but the point is that these graphs will so rarely have homomorphisms, I guess.
No.
How you can label and unlabeled.
No, it's more exact. These are C of KL is counting labeled graphs on K vertices and L edges, and yeah, any one of them. Yeah, the probability is just p to this power times 1 minus p to this power.
That's the correct thing. But the other, when you get to C star over n,
Yeah.
you're saying that you're counting and saying that those probably equal to saying that probably equal to a structure which has K comma L. That they should come. That probably approximately equal.
I don't think I assumed that, but we can talk later. Yeah. We can talk later. Sorry, say again. How accurately can I compute it? You mean getting an error?
Yeah.
Right now, not very accurately. I'm computing I'm getting the right constants. Yeah. I have not looked at the second order term yet, but certainly I'd like to do that. And I should say that Bender, McKay, and Canfield have a more elaborate result where they have lower order terms. And I'm not saying I can't do that, but I haven't done it. Yeah, it hasn't been done. Yeah. Natural question, though. Yeah. This question is, what if C is not a constant? If C is bigger than a constant, like C is, say, root log n over n or something like that, I think that this procedure not only goes through, but it's actually a lot easier because the drift is extremely high going up and really going to infinity and extremely negative going down. And I think this will go through if C goes to plus infinity and will give much simpler results. However, if C goes to 1, where Bender, McKay, and Canfield have all the results, that's an excellent question, and I'm not quite sure of the technical things. A lot of this independence with the left side and the right side in the middle, as C gets closer and closer to 1, the left side and the right side get bigger and bigger, and the middle's starting to get squeezed out. So that I don't know.